say we move. Let's say that period t minus 1, here where you have 0, 1, right? So constant and so on. Let's say period t 0, 1, I am in a constant. So that's the state variable. So that's 0. So let's look at t period t. Right? So here, well, the probability that I, so now this is the state. Right? So here we know that we are in period 1. So if I want to know, right, so here with, so that is state 0, this is the state, well, the states that we have here was consonant, here was 1. Let's take the block of the band ones with me. Right, so that is C and B. So we are in consonant. What is the probability that I am in the consonant next period? Is 0. 0. Right, so I am in the consonant and I stay in the consonant. And then the probability that I am actually, I start in the consonant and go to vowel is P0. 1. So that is what we have. So P0. 1. So that is what we have. So I know where I was and then I go, so I was here, so 0, I may go to stay at 0, or may go to 1. So that's just the first row that matters. Now how can I actually get that? So that will be, so let's call this is the state in here in T minus 1, right? So I will this and that. And this one is indeed the first row. So I can write that as P times ST minus 1. Right. These are the probabilities that I am in the next, well, so let's do the multiplication. So that will be P00, P01, P10, P11 times 10. So this times that gives me that. This so let's change this. Right? So I can actually have a prime. Okay. Then I will get it. Right? Well, I could pre-multiply, post-multiply, something like that. Right? So then I get basically the next, probability. So it will be this. Right? So well, let's say now make it a little bit further. So here then I have the probabilities, and after one period I am in some state. So either this and that. So if I want the probabilities at the next period, alright, so well, let's say we go to the next one, the t plus 1. Then I don't know whether I was, well, let's say I'm here, right? And I know something about t minus 1, and I want to know the probabilities in 1 and 7. Okay? Then what happens is that, so if the probabilities in next period are looking like so, right? So that's the inverse. So these are, well, let's call them PT, right? From T, we can estimate like this. So I can indeed go on and then iterate once more and get the probabilities at T plus 1. In which state I am. So I sort of multiply this P once more. So well, P actually, I mean, the transition that it does is that takes me 1 step ahead. I can apply it twice and I will have 2 steps ahead. So that I can, and I can go on and on, right? But so to speak, I can write an equation that tells me what is the probabilities that I will have, I will be in a certain state when I know, say, here t minus 1, I was at, say, consonant, then what is the probability that I'm at a consonant after 2 periods, or 3 periods, or s periods? Right? So I can actually write this sort of recursively, so to speak. This will be pt times pt, so that will be to the power of 2 times st minus 1. That will be 2 is subset. Well, let's maybe go and then calculate these transition probabilities. Sort of, so now I'm calling them transition probabilities. All right. Okay. And let's see how they sort of continue as time passes. All right. Well, I mean, oftentimes we don't know in which state we are. So there's a probability that, well, let's say today I know the probability of 5.5, I am in state 1, and the probability of 0.5, I am in state 2, so I'm in one of them. Okay. So let's say that we initiate these probabilities, I will call it P0. And then let's say this P0 be simply the initial distribution of my prior, what I know, with respect to which probability I was in which state. Yeah? So these are 1, 7. Yeah? So that is what we have. So that's P0. I will define it as an array of NP, well, let's say array of, well, let's say they are equally, sort of equal probabilities. So 1, 7. Alright, so 1, 7. So there's 2, 3, 4, 5, 6, 7. Alright, so that's the initial distribution of the probabilities that I have. Right, so that's a NumPy array, and that has these values, 1 over 7. Right. We'll probably go 1 over 7 at some point in time in 0, which is the beginning of the time t equals 0. Then I'm here. Right? Now let's basically look at P, the probabilities at period t. Right? So that's sort of what we have. And let's call this, what did I say? So here, well, let's say P at period t, so let's call it pt. But in the beginning is P0. Right. Now let's say for I in the range of, say 30, I go ahead and then see where I am. Right, so in here I will have, let's call this, so that's the distribution, right? Let's call it list. Alright, so that is the list. And then let's say we have a P0, that is easier to understand. Well, let's say we start at these probabilities. We don't know much, right? So and this is first P0. Okay. So that's the distribution. Now we can basically calculate PT next period by multiplying itself. Alright, so let's call it PT by the transition probability. Alright, so let's do that. So I mean, that is the transition probability. Well, here I didn't start with a 0, 1 right off, alright, but I started with initial probabilities. Right, so these probabilities that we have in the very beginning. priors with respect to which state you have, and I'm saying, all right, so I mean, steps of 1/7 in each of those. All right. And now let's sort of do this distribution. So I have a list. All right. I will append with this PT. Clear? All right. So here this list starts with a P0, and next time it will be P0 times P, and so on and so forth. So sort of I'm appending to all of this probability, or sort of this distribution, all of the PT to the power of 2, PT to the power of 3, PT to the power of P to the power of 3, and so on and so forth, right? And I post multiply. Right? So, well, here I needed PT times that, so I post multiply, so I don't need to do the translation. So I get the probabilities in these brackets, right? So not P times PT, but other way around. Right? And that's a column. This is 7 by 7, this is 1, this is 7 by 1, so it will be essentially root 2. Alright. So, and then let's just run it just to make sure that it works. Alright, so that's the distribution. Alright, so sort of the T's at different time periods. Alright, so let's look at this. And that is how it looks like. First we have this, and then we go on and on. Alright, so that's sort of what we have. So let's look at the first number. Alright, so these are all of the matrices. So with the probability of 1/7, I start with the determiner. Alright. And then sort of there is some probability that I will be still a determiner. Alright, after one sort of I started the determiner, but then I may be a determiner in the next state. I may still be a determiner in the next state, so that's sort of what we have. Alright, as probabilities. And so on and so forth. But this probability actually drops. It becomes a smaller and smaller. Well, after what I go to 30 periods, then the probability that I started at the determiner, still a determiner is very small. That is what happens. Can you hear what I'm doing? Or what I'm telling you? Right? So with the probability of 1/7, I start my sentence with the determiner. Right? And I want to know if I choose randomly, so if you have a distribution, right? So that's not a real language model, but rather we have a real language, but rather it's a model thereof. Right? With the probability of 1/7, if I am a determiner, I stay a determiner. Right? And then 1/7 times 1/7 and so on and so forth. Right? So I may go out, but then I may come back to it. It doesn't matter. It doesn't work that I come back to the determiner. Because whenever we have a determiner, then we were going out. Right? So where will this probability actually converge to? When I have actually, let's increase this by a very large number. All right. So instead of 30, let's say we have 300. All right. So I'm going to redo that. Okay. And that's done. And let's look at the distribution. All right. So that sort of goes and becomes smaller and smaller. Right. So that is what we have. It's not totally zero, so that is actually a noun. This is a verb. This is, and so on and so forth. So these are after 300 steps, and you randomly choose, then you will be in some probabilities. Right? That's sort of what we essentially see. Right? So now, I mean, the thing is that, well, let's look at these numbers. They become very small. In the beginning, they were changing strongly. So from 1/7 to 0.14, it was becoming a smaller number, right? So like 2%, then 0.03, and so on and so forth. So sort of these probabilities were coming and becoming smaller and smaller. But let's look at this probability. What what we are calculating. So here we are saying PT plus 1 equals PT times P. Right? So this sort of you update the probabilities of being in some state as time passes. Right? As you basically go ahead. And after some time, these two will not change. Right? So that will be like a fixed point. So you are at some probabilities and you do not actually change the probabilities anymore. Right? So these are the probabilities that begin after going ahead and choosing these determiners, verbs, adjectives, and so on and so forth. We call them the steady state probabilities. Right? The steady state probabilities are in such a way that you have essentially these going off. That's P equals P times P. Because after some time periods, and there is no change in this probability. They stay the same. So these are what we call them the steady state probabilities. Let's go back to here, to this simpler means question made it very hard for me to explain in many states. But let's just stay with this. So that may be a little bit easier. So that will be, say, PT plus 1 equals PT times these transition matrix. Right? As we have them, and then we go on. Because these are 7, I can't plot them. That would be very problematic. Are you happy if I do this with 2 states? I mean, yes. So that we can plot and see and what it is, all right? This I will post online. All right, so let's have another basically little program. So here I will have the NumPy and so on and so forth. All right. So that is what I have. Let's calculate the probabilities and sort of put the probabilities. Right? So well, let's we didn't calculate them from the sentence that Lynn wrote for us, but I'll just put some numbers. Right? So then we continue with it. Right? So let's say NP array of well, let's say you're a vowel, and then with 30% you stay a vowel, roughly, and then with 70% you go to consonant. And when you are a consonant, then you leave it with probability of 0.55, and then you stay a consonant with this probability. Right? So that's a little bit easier to deal with. Alright. Let's do these calculations again here, like we have. Alright. So but with a smaller transition probability. So here I have P0, and then let's say this is 0.5 and 0.5, so very rough. We need the starting point, then I have P0, and then I go on, let's say, 30. Alright, so these are the probabilities. And what I want to plot, I will just now go and plot these guys, and so that we see them. We see what happens to them. The elements of this distribution. So that is what we have. So PLT dot plot. Right? So here we have this. I call it this. And I look at the first element. Right? So well, let's keep in mind. So what it was. This is we start from a V. From a vowel, and this is we start from a consonant. Right? So we start from a consonant and then a steady consonant with a 45% probability and so on and so forth. So we understand this probability distribution. Fine. So, and then let's also plot the other probabilities. Start 1, then PLT dot plot. Let's add labels so that we understand them. So that will be a V. That's the first element.
have the list, or rather have NumPy. I don't know. DBO. There's another map. Alright, let's have it the list, but later we change it to an array. So here we said this is equal to NumPy array of this. Okay, how it works. Now let's look at it. Well,
Yeah, you see, so somehow I understand how Python works, but
I have to get it right.
let's look at these guys, right? So here we have 0.55, so that's the beginning, alright? And then, well, I mean, so if I am with a 50% vowel, then I sort of will be still in a vowel, but it's with a smaller probability of 0.5. And it goes up and down, so a little bit, and after some time then it becomes fixed, it doesn't change anymore, right? Because we are, well, soon after sort of some iterations, then we follow this steady state and we don't move anymore, alright? Clear?
Yeah, so that's sort of what we have. And these values that we have, so that is what we have in the very end. Alright?
So this is the probability that you are in a vowel and stay in a vowel in the long run. Alright? So indeed that will become the fraction of the vowels and the fraction of the consonants in the whole sentence, because that's a steady state. It means that you write a very long sentence, all right? And you start with some starting probabilities, like 0.5 and 0.5, that you are, actually this 0.5, 0.5 don't matter, all right? If I start from, say, 0.3 and 0.7, then I will still converge into this, because, well, the eigenvalues of this will be small, such that the initialization of this process, that's a difference equation, doesn't matter, vanishes like an alarm. So that's sort of how we can solve for the steady state probabilities, and they tell us how, well, the fraction of the consonants and the fraction of the vowels of the different vowels. Can you understand this? Maybe I should let you talk to me. Yeah. So you ask me please questions. Yes. Me.
Okay, so basically we solve for this, we solve this equation for the steady state.
That's true.
And,
Numerically.
in here, right, we just assume that we have some kind of like priority and you
Yes.
plug in, right? But what if it's not a fixed number?
The beginning.
Yeah, it's like the beginning, maybe like you put in some sort of like distribution, then what might happen?
The beginning actually disappears. Let's change from 0.5 and 0.5. Let's change to 0.2 and 0.8. Yeah? The beginning doesn't matter. So let's say we have,
And then, but remember, these numbers are what I'm
But then say like you either change the beginning or you change the structure of your P, right? Then how would it affect like how fast you will converge to the steady state?
well, that depends on the eigenvalues. We will now do the algebra. So the convergence, actually, well, I mean, so if the eigenvalues are small, then the convergence will be very fast. But if the eigenvalues of P are small, if they are large, close to 1, then the convergence will be very slow. It is pretty much like the AR models. So the autocorrelation actually drops to 0, all right, very fast when the AR coefficient is very small. And then slowly goes to 0 when the AR coefficient is very large, close to 1, right? So that's the same. Let's maybe, wait, let's do it with 0.2 and 0.8, and then we see. So
sort of, I mean, we start with 0.2 and 0.8, and then sort of after a very short period of time, then we converge again. Because the eigenvalues of P are the same, and they are the ones which govern when you converge, or sort of the speed of convergence. All right. Well, P is generally given, so we know, well, I mean, sort of from the sentences, we can basically count, sort of calculate the probability that I'm in a C and what is that I land in a V. Right? So 0, 1. These probabilities we can always get estimate. Right? So from the data. So these are data. Right? Or from the sentences, we can also go and calculate the probabilities that you are studying in the terminals. So what is the probability that you go to well, let's say a noun is followed by an adjective. Somebody told me the probability is 0. So this is something from data we can learn, we can get. Right? This, the elements of the transition probability we can get. And longer sort of probabilities, we can also, once I have this, then I can solve this equation. Can we solve this? Sorry? Pi. Solve for pi. So solve for the steady state probability. Well, that's an equation. Right? So this I can take to the other side. I can have pi identity matrix minus p equals 0. So, well, I mean, then this is actually, so this should be orthogonal to that. So you remember how we calculate the eigenvalues of an eigenvectors. Right? So of a matrix. So we can actually go on and now solve for this. But now we're not interested in all of the eigenvectors, right? But rather only, well, I mean, we need these probabilities to be positive, and then they have to add up to 1. Right? So we have this pi times, well, if it is a vector, times a vector of 1 prime should be 1. Right? So they have to add up to 1. Right? So, well, the equation that we have is indeed these twos together. Alright. We have to solve this one or rather the other. So to speak, if I solve this, then I wish to have these guys to be normalized to 1. When they add up to 1. Alright. We can solve it using, you know how to calculate the eigenvalues. No? Oh. And do you know what is an eigenvalue?
Yes.
And what is an eigenvector?
Yeah.
Do you know that? So I got an eigenvector for a square positive definite matrix or somewhat definite matrix. And I have one. So for a square matrix, an eigenvector is a vector that if you multiply it by that, then it stays the same. Direction doesn't change. An eigenvalue is the scale. So the vector may go longer or shorter, or change the direction if you have negative definite matrices. Alright? Okay. So well, let me discuss the definition, sort of the algebra of getting the eigenvectors, eigenvalues when I come to factors, to the principal component points. Alright? So here I will tell you how to do that. Well, numerically, you know, but maybe using Python. Alright? So that will be sort of just to solve this equation in Python. should be 1. Right? So these are two equations that we have. So I can actually take the first, so I can rewrite this as I go there. Then will be pi minus p equals 0, and pi times 1 prime equals 1. So there are two equations that we basically want to find pi for it. Right? What we can do is the following. So you can indeed, it doesn't matter if it is I minus p or p minus I. But let's say we put this matrix P somewhere here. Right? So that is P minus I. And then here we have a vector of 1. Alright, so well, that is what we have. Times P transpose, it is indeed zeros and a 1. So now if I want to solve this, then you know how to solve it, right? So that's a simple linear equation. So in Python, then we can use the function solve, right, to solve this basically matrix equation. But let me just implement it. For you. So well, let's define this matrix that we have here as A. Alright. Right. So let's say we have A. So here, this is 1 prime, so it is transposed. Well, and then here I have a transposition. So then, but here I didn't transpose. So let's transpose this. Alright. So that this is indeed okay. That becomes a row vector. So that's a row vector. And that's also why I transpose it, multiply by p equal that, so that you have all of the dimensions of the equation correct. When you are at home, check this. Okay. That this is indeed okay. So here then I'm going to have np. So let's transpose p minus np dot I of, well, what is dimension 2? That is what we have. And then let's say we have np, well, that's A. So that is okay. So now I need to add these ones below. Stack it below that. So I'm going to have essentially, that's a vertical, so it comes from below. So that's a stack vertical of A with a numpy of 1s of dimension 2. Okay. So that's sort of what I have. And I have to pass this as a list. Okay. So that is A. And let's look at A. That is how it looks like. So these are the transition probabilities. Alright. So 1 minus, so I turned it, sort of like took it to the other side. So that is 0.3 minus 1.7. So, and that is 0.7 as is. That is 55 as is. And this is 45 minus 1. So this value. And then I have the two values, 1 and 1 down there. So that's my A matrix. Well, this one multiplied by P equals that. Equals a 1. Alright. So, well, now, well, I mean, the left-hand side that we have is, well, I'm just calling it A because like A x equals B. Alright. That is a, well, equation that we have seen before. But let's define also B. So B indeed just have 1 in the very last element. Alright, so that's, all of them are zeros. So here I will have a numpy of zeros of dimension 3. But the last element I will set to 1. Alright, so that is what we have. Good? And now this you know how to solve, right? Well, this we can indeed multiply by A prime for x becomes a times a minus 1 a prime b. But x prime x, x prime y. That is what you know from OS. But it comes from algebra. Okay? So, and that is what we have. And now let's generate the steady state probabilities. Steady state probabilities. That will be the solve essentially. So that is the solver. Well, I mean, solver you can bring in, so that is actually easier. So from NumPy, when it has the linear algebra, it will be our friend very soon. Lin from NumPy. There is this section which is called lin alg. Alright. From that we import the function which is called solve. So that is what we bring in. Now I have A, I have B, and now I can go solve this. So that will be A prime, A. So that's the equation that I have on this side. But I mean, if it is invertible, then you can do this. If not, then we need this solve equation, right? So that's sort of what we have. Right? Well, it ignores essentially the problems you may have. And then A t times b. Right? So that's sort of what we solve as the steady state, so we get that. And let's look at the steady state probabilities. And they are beautiful. At 0.4 and 0.56. Right? That is what we have. And that's the last iteration. And remember that we did numerically. So that is the numerical value. It's called PT, and this is what we solved by using the linear algebra. But explicitly solving this pair of equations. So these are the steady states. And what do the steady state tell us? The steady state actually, well, I will be happy to. So, well, remember that we had well, I mean, what was the first one? Was a consonant. Let me just see. A vowel. So this is a vowel. Right? So the first row is a vowel. The first state is a vowel. The second is a consonant. So these probabilities actually tell us the fraction of vowels that we have in the text. And the fraction of the consonants that we have in the text. So 44%, right, of the letters that we have here, well, I mean, with those probabilities, with those transition probabilities that I put in, 44% will be vowels, 55, what was the rest? 56% will be consonants. So that's the long term, the steady state probabilities that we have. So this means that if you at random pick a letter from the sentence, the probability that it is a vowel is 44%. And 56, the probability that it is indeed constant, the others. So these are the longer probabilities. So far, so good. I will come back to the eigenvalue problem, because you said you don't know how to solve it later. So maybe Thursday or the last session. Right, so far so good. But these were all about going from one state to the other. It seemed not to have much with the econometrics as I had. But I think the idea should be now clear that if you're in one state, and you know what is the probability that you move to another state somehow, if you can get it from the sample, then you will be able to understand what is going on in the data, right? Actually, this Markov switching models came in econometrics with a paper in 1991, I think, with Hamilton. Hamilton's book, you know, so he has a paper where he applied this to understanding the growth rate of US. Right? So the growth rate sometimes was negative, sometimes was positive. If it is negative, was to say, right, so we have two states, contraction, expansion. And then at every given point in time, let's see what is the probability that we are in an expansion or in a contraction. So that was essentially, that is the limit to the conventions. These are all letters, and these methods could be applied to other economic, macro, and financial problems. All right. Sorry? Microphone. Sorry for Okay. The previous ones were not important. These letters and so on. From now on, that is econometrics. Put the microphone on. All right. Well, let's actually think of this in terms of econometrics stuff. All right. And let's see what can we do. Remember, we have some state variables. This is the spot price. We have some state variable, which is either regime 1 or 2. Right? So contraction, expansion, high volatility, growth, bearish, bullish, right? Or the transition period between the two periods. And you can have 3 states. You can have more states. Right? But you always remember that the more states you bring, then the more parameters. Right? That's sort of also something that you have to keep in mind. For language models, right? So these are sort of the language that we have. Then the states should be a little more. Right? So they have to be more and more so you can generate. We can now go with these probabilities that I have generate sentences in Vietnamese language. And you will laugh at them. Because they will be just not meaningful. Alright? So, well, and because we know, well, let's say you have one letter and then what is the probability that another one comes? Or generates a constant vowel stuff. You can't do that because we have the probabilities sort of. Right? So if you want to make them work and generate meaningful sentences, then you need some more models, some more language models to be in, not only counts, correct? And then when we go to econometrics, then we also need more structure, right? So that we can make up something which makes sense. Right? So if you don't mind, then I will write those. The sentences. But later it will make sense to calculate those and then check the probability. Maybe then I don't write. But let's say we have some variable. Let's say this is the GDP growth. Right? That is the problem that Hamilton solved for when the Markov models, the Markov switching models actually were born. And here you have a mean, and this mean depends on the state. Plus some shock. So that's actually very simple. Epsilon. Right. And now these states are either 0 or 1. Either you are in an expansion, mean is positive, or when another regime, mean is negative. Right? So this mu actually has 2. Well, ST can be 0, can be 1. So what does it mean? It means that mu ST can be a high or a low. Indeed, value. Mu 0 or mu 1. Mu 0 or mu 1. Right? Probability. Not only we have to estimate this mu 0 and mu 1 because we want a full estimation, but we have to also understand when is ST value. Is it with which probability high and with which probability low? Right? So the transition probabilities we have to also estimate. Okay. And let's say this shock is normally distributed. Right? Then we can write the maximum likelihood problem. Right? So because from this we observe, this we don't know. Right? With some probabilities that we are here or there. Right? Or so to speak, then the shocks are known. So these are RT minus mu ST. Right? Well, if they are independently distributed, then it will be not a big actually deal to write the maximum likelihood. Maximum likelihood will be a function of mu 0, mu 1, state probabilities. So P00 and P1. So there will be 4 parameters here to estimate. Okay? Well, let's do it actually a little bit more. Alright. More, let's do another maybe example. So that was the growth. You can also, of course, add more variables. Well, let's actually look at a CAPM regression. So here we have the risk-adjusted, risk-free adjusted maybe returns of some asset. Right? So some asset I. Then it is equal to alpha. Alright? Let's say there's a function of ST plus kappa and beta. It's also a function of ST of the market excess returns. Okay? And then you can add more. So let's say this is kappa beta. So let's say we have the beta of small minus b. Also a function of the state. And here we have the small minus b in the parameter. And then plus high minus low. Right? And then high minus low. And so on and so forth. Right? So we can bring all of the variables or the that we wish to have plus ut. Right? Close the arrow. Now, when we not only we have to estimate alphas in different states, but as I said, then we have to also understand this ST. For the rest, I mean, with this language and then vowels, consonants, determinants, I give you the idea, and now I directly take this idea to different measures. So, you were in the beginning saying, how is it possible? And now this is the how. Right. So the rest is math. So this is to write the maximum likelihood, and once we write the maximum likelihood, then we can go and then do optimizations and so on and so forth. So the rest is just mathematics, numerics. And how to bring essentially the data. Good? The small minus b. Oh, you don't know the factor models? The Cap and Fama French? 5 factors? Look, so a small minus b is that when we say you have a market, and the market in some companies are big, some are small in terms of size. Right? So here, well, let's say we sort them based on the size, and then well, let's say there are 500 companies, and then we look at the average returns of the smallest ones. Let's say the last 5 on the list, sort of from big to small. So small is down, minus the average return of those that are big. So that's a size effect. So sort of the big and the small, how do they move with respect to themselves? So that's the size, how big they are. High minus low is that you look at the returns, regardless of the size, of all of these assets. Right? Again, say 500, the size doesn't matter. And then we sort them. High are on top, high returns, and low returns are below. So that will be the average returns of the best performing companies in the market minus the low. The lowest performing companies. Okay, so that will be a measure of, because if there is actually a lot of differences, right? So in terms of the returns in high minus low, then it means what? It means that there are some very good performing companies, some very bad performing companies. So some are more risky, some are less risky. And that means that there is, well, you don't know what to do. So that's sort of the market is targeted if this high minus low is high. If they are close to each other, then there is not much of variation. So sort of the market is okay. It sort of doesn't move too much. So sort of things are stable. So times that this high minus low actually move on and on. And then we have the other factors. Maybe we should estimate we'll estimate these 5 factors models. Maybe in the afternoon. Right? for, with the Markov switching model. All right. And now, well, I mean, pay attention to this. All right. Look, this is alpha. This is the kappa, the usual kappa and beta, and then these are the prices of all of those factors. All right. So that's sort of what we have. Okay, let's look at that. All right. Specific. So that's a function of time. All right. This time varying. Goes up and down, depending on the states. All right. So, which is actually interesting. So somehow nice because I mean, sort of it gives us some time varying in the components in kappa and beta, which is sort of, as I say, interesting. So time varying components we did estimate before in the rolling windows in framework. Right? So that's another way. That's another way of understanding time variation. These are not the best ones, but there are some. Alright? Actually, there is another one which is Kalman filters, sort of a state space indeed modeling. Similar to this, but a little bit different. Alright, so because we have some state variables, and then we condition on them, and then we go on and on, but that's sort of slightly different than modeling approach. That also is capable of capturing time variation. Alright, but let's maybe stay with this for our purposes. Okay. Now, before I do an application, I want to give you a bit of theory. So, not on a regression model, but rather on a more simple setup. Right? So regressions could be a little bit tricky because of the condition expectations and so on and so forth. Right? So you understand essentially how these models work. So you write the likelihood in the function. So now I don't want to write it. So let's stay with that. And let's say we have a variable xt. Okay? And the variable xt is always normally distributed. Alright? It's always normal. But depending on time, then sometimes it has a higher mean, sometimes it has a lower mean. Alright? But sometimes it also has a higher variance, sometimes it has a lower variance. So to speak, we have two states. Alright? So here, this is normally distributed. Alright? And it is independently normally distributed, but not IID. Right? So this is not independently identically distributed. It was one of the i's. It's just independently distributed. With mean, ST, and variance also as a function of the state. Right? And then let's say these states, well, the states are also independent. Right? So they are independent, we choose to be in this state or the other. Right? And then we have some data on this. So it's T observed. T from 1 to T. Right? And then we want to go on and from the sample write the likelihood function and then see what is mu1. Let's say the number of states is 2. Otherwise there's a lot of parameters to this. So here the number of the states is 2. So there are not many. That will be very easy. So the number of states is 2. Now, well here I want that you pay attention to the fact that not only the mean or the parameters of the conditional mean can be dependent on the state variable, but also the variance of the residual. It also can switch between the states. Can be fixed, can be switched. Well, in the kappa model, it makes sense to have the variance actually switch. Because, let's say kappa beta is high or low. When it is high, then it's more